my pleasure to welcome Virginia Agostiniani from Trento, and she will talk about on the mass of Riemannian free manifolds with a positive curvature lower.
Thank you very much, Esther. Thank you really very much for the organization of this nice conference and all the effort that you have put in it. So it's a pleasure to be here. Can you all hear me? Okay. So yes, this is a joint work with Stefano Borghini, who is now in Napoli, Federico II and Lorenzo Mazzieri from Trento. Some of the results that I'm going to talk about are very, very recent of the last weeks. Okay, let me start. Since all these talk, as you will see, will be around a model space, a model manifold. So let me introduce it before the rest of the talk. So let me start. So the model space we are talking about is the de Sitter spatial manifold, and let me derive this de Sitter as a slice of the de Sitter space-time. The de Sitter spatial manifold, you can also if you are more familiar with it, call it round hemisphere metric, essentially. But it's better for this talk, which is very much related with general relativity, to derive it as a slice of the de Sitter space-time. So the de Sitter space-time is a one-sheet hyperboloid, okay, into in R5, okay, and a way to introduce this metric is to induce on this one-sheet hyperboloid the Minkowski metric of R5. And so let's look at some slides or at some coordinate in which you can express. For example, if you choose one coordinate as this function, so the inverse function of the hyperbolic sign of the x5, then you can do on the de Sitter space-time this slicing. So these are global coordinates which give rise to slices that are closed. But another possibility is to do what is called static, to use static coordinates. In this case, they are not global coordinates, so they give rise to what they call static patches. And you can see here one of these patches. And and if you use these coordinates here, you can rewrite the de Sitter space-time in this form, okay? And this yellow part here, bright yellow part, is the three-dimensional spatial de Sitter that will be part of my talk, okay? In this picture, which is a two-dimensionless picture, this is the metric on each of these half of S1, okay? As you cannot see from here, okay, but actually this is a static metric, so that means that on each slice, on each black slice, I have the same metric. It doesn't seem from this picture, but actually all of these arches have the same metric, okay, which is the 3D spatial de Sitter, or if you prefer, round hemisphere metric, okay. We'll go, look at it again later, okay? Now let me give a summary of this talk. I will talk a little bit about the state of the art regarding the seek of an appropriate concept of mass, of total mass in the setting of three-dimensional manifold with the scalar curvature lower bound, strict lower bound. And I will say we'll talk about a series of results in the opposite way in which they have been obtained. So we'll start by the end. And so I will really introduce the very last things that we found in the last weeks. That is what we call the one harmonic mass in the setting that I was describing, providing a positive mass theorem for this one harmonic mass. And also, we have understood that it also satisfies in an unsuitable setting, the Riemannian-Penrose inequality setting, the Riemannian-Penrose inequality. And then I will show, and this was the part that was more computationally important in our work. The reason why we found out this very nice total mass that are new was in the limit of some p-harmonic masses. So I will describe the formal limit of some p-harmonic masses to the one harmonic mass, and if time permits, I will also show you how really we arrived to this construction of these p-harmonic total masses. Okay, so let's start from the beginning. I think that in this audience there's no need to stay longer on this slide, so let me just recall you briefly that this lower bound for the space-like hypersurface inside space-time comes from a coupling of the Einstein field equation and so a ball of the Einstein constraint equation with the dominant energy condition and the hypothesis that we are in the time symmetric case, that is the second fundamental form of my space-like hypersurface is zero inside the space-time. So if you translate the dominant energy condition, that is that the matter energy density dominates the magnitude of the momentum density, you obtain this lower bound of the scalar curvature of the space-like hypersurface. Okay, lambda is the cosmological constant, so we prefer to write 2 lambda. Okay, we do this. It's normal to do this formalization. Okay, so throughout, I will talk about this setting. So, but before talking about the case lambda positive, now let me review a little bit what is known about the case lambda equal to 0. Okay, so let me recall the famous positive mass theorem in the setting of lambda equal to 0. Okay, the lambda equal to 0 case means that the scalar curvature is bounded below by 0. The classical setting is the one of an asymptotically flat manifold. Attached to this manifold, there is this notion of mass developed by three physicists, Arnovit, Denzer, and Missner. And remember that inside you see there are all these derivatives of the matrix. So the positive mass theorem, this is the famous statement. So the mass, the total mass, ADM mass is non-negative, and it is equal to 0 if and only if the manifold is the Euclidean manifold. So here I recalled the various proof of this seminal result, starting from the first one given by Shenyao with the stable minimal surfaces, and passing through Wisken-Hillman and through the weak inverse mean curvature law. Let me cite it in particular because it is the one among these contribution that is more closer to also our concept. But let me go on. So let me say that the hypothesis under which the theorem can be proved are the optimal hypotheses, in the sense that are exactly the one under which under the decay condition under which we can prove one can prove the theorem are optimal, in the sense that are all the same condition through which the ADM mass is well defined invariance. That means it does not depend on the coordinate chart at infinity, which are these asymptotics. Okay, so the decay rate towards the Euclidean must be like that. Okay, so let me say also that in particular, if you look now at this definition, what you have, since you have a positive mass theorem, that if the metric goes to the Euclidean metric sufficiently fast, it's clear from the definition of the ADM that then the mass will go to be 0, and then the space will be flat. So in the same sort of spirit, then Minot proposed and proved this theorem also for asymptotically hyperbolic space. So if you have a strongly asymptotically hyperbolic space, okay, then it must be isometric through the hyperbolic space. I say this because then, okay, in the case lambda negative, when the constant, homological constant is negative, various concepts of masses were developed, and then also corresponding positive mass theorem and so on. But this was completely missing in the case of lambda strictly positive. Okay, this is why following a similar argument, a similar way of thinking, Minot proposed the famous conjecture for the case lambda positive. Okay, so suppose that now R is bounded below by the positive constant, which is now normalized to 3. Okay, so 2 times lambda here is 6. And suppose that at the boundary, okay, of this hemisphere, you are the metric, the S2 metric, okay? So you really are equal to the metric at the boundary of the model space, and also suppose that the second fundamental form is 0. Okay. Now look that here this boundary is a sort of asymptotically flat boundary at infinity, meaning that these two conditions translates the fact of being strongly asymptotically flat. Okay, because for example. In terms of a distal coordinate, you remember that the second fundamental form is the derivative, no? 1/2 the derivative of Gij. And so this this is the connection also with this. So the Minot conjecture was saying that so if you are on the closed hemisphere and you put in it a metric with this precondition, then the hemisphere must be the round hemisphere or the de Sitter manifold. But this was not true, because in fact the conjecture was disproved by this very beautiful paper by Bredl, Marquez and Nevers in 2011. They proved that there exists a smooth metric G. Actually, there are many of them of the hemisphere with the following property. So they satisfy actually the three conditions that they were before. So the scalar curvature is bounded below by 6, but also you cannot identify it with the model solution, because there is at least one point, the orange point on which the scalar curvature is strictly greater than 6. So it cannot be the model solution, because the model solution has scalar curvature constantly equal to 6. Okay, and at the boundary, not only just at the boundary, but in a neighborhood of the boundary, it coincides with the round hemisphere metric. But so even in this case, so you can find exactly one manifold that is not the model solution. Okay. Okay, so on the positive side, so let me just mention that even if they are not really in the spirit of what we are looking for, because now we are looking for a good definition of mass. So we really want to stick to the original setting. So we don't want to put other hypotheses on the setting in order to force the manifold to be the model manifold. This is instead more or less the idea beyond this, behind these results. For example, with condition can we indeed prove that the conjecture is true? So it was proved by Han Wang in 2006, restricting to conformal, to metrics that are conformal to the round metric. Then again, by Han Wang, it was faced the same problem. So with a positive answer, when in place of the scalar curvature lower bound, you have a Ricci lower bound. Then Heckmeyer proved the Minot conjecture as a consequence of some result of his regarding Ricci positive, Ricci strictly positive 3 manifold with scalar curvature bounded by 6, admitting isoperimetric surfaces. And then also Bredl and Marquez proved the same conjecture, but if you take a spherical cap, okay, if you put the same condition but on a spherical cap which does not arrive at the equator, so with a radius less than pi/2, okay, means that you have a spherical cap, a smaller spherical cap, okay. Okay, then there was also this result by Spiegel, who improved the result of Wang on conformal round metric, replacing the condition of being conformal with being locally conformally flat. Okay. Okay, now let me say something more regarding the setting we are more interested in. So the seek for a good concept of mass. Okay. So clearly here, in the setting of positive scalar curvature, there was not something available. So one tries to look in the places where it can give you some positive answers. So for example, in the case of lambda equal to 0, a good mass starting with is the Hawking mass and the good flow on which one can maybe prove some monotonicity is the inverse mean curvature flow. So I don't think that I have to recall you about the inverse mean curvature flow, about the Hawking mass in this setting, about the Jerox computation, and how in the paper of Whiskey-Manel this was formalized. The concept of weak inverse mean curvature flow was introduced, and then it was proved the Riemannian Perox inequality and also the positive mass theorem. So let me say more what we can say in the case lambda greater than 0 if we try with the same objects. Okay, if we try with the same object, what we can say. So first of all, this is the version of the Hawking mass in the case where lambda is different from 0. So this probably the first appearance that we found was in this paper of Gibbons of 1999. The Jerox computation, smooth computation on this quantity along the inverse mean curvature flow, the smooth inverse mean curvature flow goes exactly in the same way, okay? And you find something that is non-negative, okay? Along the inverse mean curvature flow. But there are two problems. Okay, first of all is that the Hawking mass is not a good concept, cannot be a good concept of total mass for things like the hemisphere or things that are close to be a hemisphere, because if you compute this on the of the boundary of your manifold, the Hawking mass is 0. And at the same time, at the point where you started the inverse mean curvature flow is 0 also. So it is not a good concept of mass in the sense that for example, it gives you 0 also to the counterexample of Marquez and Neves. But so the total Hawking mass in that case is 0, but this does not characterize. This means that does not characterize the total Hawking mass being 0 does not characterize the de Sitter space or the round hemisphere space. Plus, there is also another thing that from the counterexample of Marquez and Neves, you can also say that there cannot exist in general an inverse mean curvature flow that starts from a point of your compact manifold with boundary and arrives at the boundary. Because if you suppose that this happens, you find a contradiction. Because suppose that it starts the inverse mean curvature flow from one point. So in there, the Hawking mass is 0. Then the inverse mean curvature flow start. At the end, as we said, it arrives at the boundary, and the boundary is the Hawking mass is 0. But at the same time, the derivatives at some point is positive because of the counterexample of Marquez and Neves. So at some point, the scalar curvature is strictly greater than 2 lambda. So this means that the derivative of the Hawking mass is strictly positive. So it is a contradiction. So there cannot be an inverse mean curvature flow starting from a point and arriving at the boundary in general. You cannot prescribe, say, an inverse mean curvature flow that arrives at the surface that you want. Okay, so the inverse mean curvature flow was not a good idea, and what I'm going to tell you now is that at the very end of the story, what we found is that it's a good substitute for the inverse mean curvature flow is a new concept which is introduced in the last years by Kai Xu, which is called the inverse mean curvature flow with outer obstacle. So let's go into see this from the beginning. So first of all, let me recall what is the setting. Okay, no, you take a Riemannian compact manifold with smooth boundary, and you suppose that the scalar curvature is bounded below by 2 lambda, positive lambda. Okay. So first of all, what is the reference to model that I've already mentioned many times, but so let me rewrite it here. So it's half of S3 with this de Sitter or round hemisphere metric, and the radius goes in between 0 and r lambda. Okay, as you know, here in r lambda there is not the real singularity. Okay, because the metric is perfectly smooth up to the equator. R equal to the capital R lambda correspond exactly to the equator. Okay. Now, this is the inverse mean curvature flow with the outer obstacle that I was mentioning to you. So suppose that you take a point in your manifold, okay, without the boundary, so inside, And let me call W the inverse mean curvature flow without an obstacle that originates from X. What is this thing? This is a suitable weak solution of this problem, which is written in this term to give the heuristic. Okay, so essentially W, and so is exactly, so it's the solution of grad W equal to the mean curvature outside the points, and but okay, this is in common, okay, with the case of the inverse mean curvature flow. What is different is the boundary condition. Okay, so prescribing a Dirichlet boundary condition, we have somehow understood this from what I said before, but in Kaik-Su also explicitly says that the Dirichlet problem in this case is not well posed. So it has to give this condition here. So this means that the level set, when it arrives at the boundary of your manifold, the normal to the level set must coincide with the normal. It's the normal of the boundary. In other words, when the level set arrives at the boundary, it sticks to it tangentially. Okay, like in this picture. Okay, this is a picture taken from the original paper of Kaik-Su, very nice. So here is the flow starting from this black point. In this case, you have also a hole in your flat manifold. This is another picture that is more in the sound of what we are doing in this talk. And here also, okay, this is more like a flat drawing. Again, the flow starts from here, and here I wanted to underline those two specific times that will be relevant in a subsequent analysis. The time that we call T under star, okay, and D and T star above, okay, which are the first time where the flow, the inverse mean curvature flow with obstacle touches the boundary, as you can see now. When you start from this black point, the green one is the first level set touching the boundary, and this red one is the last. Okay, so remember this because it is contained in the next definition of the one harmonic map. Okay, so you defined the T lower star and T upper star, as I said. And you also define this strange parameter that is not so strange because it's really coincide with the touching time of the reference model, and we call it capital T lambda. Because, as you are going to see also next, the model solution of the inverse mean curvature flow with obstacle in terms of the coordinate r is 2 log of r. So this is exactly the moment where the flow touches the boundary, which coincides to r equal to capital R lambda. Okay, and so the one harmonic mass is this. You see in there is the perimeter of omega tau. Omega tau is the sub-level of your flow function, and Tx plus is the minimum in between this parameter T lambda and T upper star. Okay. Okay, this is the one harmonic one. The fact is that it was very difficult to arrive to something like that from anything. So we could arrive to it, and I'm going to show that we hope it is a relevant quantity because it satisfies nice theorems. We could arrive to it just from the analysis, quite as I said, computationally important analysis done at the P level. So as we are going to see next, hopefully, introducing a suitable P harmonic function and finding this mass as the formal limit of some P masses. But let's talk about this later. So here I've just recalled the main point of the construction. You're in your manifold, you have a point inside your manifold, you start this inverse mean curvature flow without an obstacle due to Kaik-Su, and you define the one harmonic mass here along the level set of the inverse mean curvature flow, okay, up to this threshold Tx plus. Okay, this mass has good properties. First of all, the first check is that the mass is 0 on the model solution. And this is just a simple computation to show you this. Okay, as I was saying before, when you are in the model case and you pick as a starting point the North Pole, this is the exact solution of the inverse mean curvature flow without an obstacle. It's 2 log of r. And so you compute all the ingredients to put inside the mass for the model case, you end up with very nice, simple integral that you discover to be 0. Okay, so the one harmonic mass on the model space is 0. Okay, first check is okay. But it's not enough. Actually, it satisfies the positive mass theory. It's also characterized. So if you are on the model space, the mass is 0, but also vice versa. If the mass is 0, then your space is the de Sitter. It's exactly what the total Hawking mass doesn't do. Okay? So suppose that you have a compact free manifold with the scalar curvature bounded below by 2 lambda positive, and suppose that the boundary is minimal and it is simply connected and unstable. And also suppose that there are no other closed minimal surfaces in M minus the boundary. Okay. So consider that these are exactly equivalent to the condition of the positive mass theory proved by Wiskelin-Mannen. Because if you think of the asymptotically flat end, okay, the asymptotically flat end is foliated by not minimal but constant mean curvature, actually spheres. So in particular, they simply connecting. Okay, so they are not foliated with minimal, but okay, with constant mean curvature, with a constant mean curvature that is going to 0 at the very end, no? Because they are big spheres. And also unstable, because the very last end is unstable because the area of the ball of this constant mean curvature surface is just before it is a bit less than it, right? So it's really correspondent. And also this is one of the ingredients of the proof of the Wiskelin-Mannen, the fact that there were no other minimal surfaces inside. This also gives you that essentially the topology of your manifold is quite simple, and this allowed essentially to prove some monotonicity of our formulas, like in the proof of Wiskelin-Mannen, because we need the level set of our flow to be connected in order to apply some the Gauss-Bonnet theorem. Okay, but so these were the hypotheses, and so this is the thesis. The one harmonic mass is non-negative, and it characterizes the de Sitter metric, the lambda de Sitter metric for the round hemisphere metric. Okay, so I prepared also some slides about the proof, but I think it's better to skip them, even if it is quite quick, I have to say. So let me skip these, because I also wanted to mention the fact that we have also a Riemannian Penrose inequality satisfied by our one harmonic mass. Okay, so let's now discuss a little bit the setting, which is just a little bit different with respect to the setting of the positive mass theorem. Because in this case, there is a hole that opens up in your manifold. In fact, in the setting, in this case, is a setting of, differently from the positive mass theorem, we have 2 boundaries, okay? So the boundary is disconnected into 2 pieces that we call boundary of M minus and boundary of M plus. The boundary of M minus is the one that has less area, like what happens in the model case, because in the model case of this general 3 manifold with curvature bounded by 2 lambda and with that features is the Schwarzschild de Sitter spatial manifold. And so we have 2 boundaries. The boundaries corresponding to the biggest radius, R plus lambda, which is called the cosmological boundary, which is the same boundary as the de Sitter. Okay, but now there is another boundary, which is the black hole boundary, the green boundary, okay, which is in the model the one that has less area. Okay, and this is a way to write this metric. Okay, so now, as you see, depends on parameter lambda, but also the parameter m. Okay, this little parameter m is the mass of this manifold. Okay, so now, let me again introduce the inverse mean curvature flow also in this setting. In this case, this inverse mean curvature flow with outer obstacle of type 2 will not start from a point, like in the case of the positive mass theorem. We start from the the black hole type boundary. So the boundary boundary M minus. Okay, and we'll start having exactly this value. Why? What is this parameter T minus? This parameter T minus is exactly the initial time of the model solution in the case you plug in this M, the model space, okay? And so, and there is exactly the same boundary condition as before, okay? So, again, this is the version of the one harmonic mass in this context. So it is exactly the same as before, but there is also this normalization with the Hawking mass of the boundary minus. Okay. There is also sorry,
this mass is somewhat non-local, right?
Yeah, exactly. It's also it's non-local in the sense.
Not computed at infinity.
Very good. Thank you, Felix, for saying this, because it is a very important point. That when we develop, we also worked with the case lambda equal to 0, no? But okay, you can just think of the Hawking mass, no? It is defined, but also some p version of it that we studied at some point. They're just some integral terms on the defined on these level surfaces. Then no, you make t tending to plus infinity. But in here there's always a bulk term. So the mass really sweep out all the manifolds.
It sounds a bit unphysical. Each longer, people just sort of observe something from infinity.
Yes, but you have to take into account, for example, in this manifold, you have to take into account what is, because it is also a compact manifold. Also, for example, the pole where you start, no? If you start from any pole, in the case of lambda equal to 0, it doesn't make a difference, no? Because the mass is defined at infinity, it doesn't make a difference if you start from here or to here. But here we are in a compact manifold. Also, we have this lambda positive. And so in these energies, yes, there is always a bulk term. Okay, that we have to move that. Okay, so maybe later we'll see the p version of these quantities, and this thing that we were discussing with Felix will be clearer. Okay, so this is the setting. This was just a slide to define to you these two quantities here, these two time, essentially t plus. Okay, it is essentially well defined only if this R minus here, the R minus, okay, I haven't defined here, so it's better if I skip this part because it is a bit technical, but let me just say that it is a one important thing, that if you look at the model, okay, what are these two R here? The two R, capital R, lambda minus, capital R, lambda plus, are the two roots of this, right? Of this denominator. And you have exactly two roots, which is equivalent to say that this equation P lambda R equal to M is satisfied by R, only if M is in between 0 and 1/3 square root of lambda. Okay, so M must be a parameter varying in this range. Okay, so and also for this T plus being well defined, we have to observe something about this graph, but I'm not going to say this now. Let me just say very briefly that clearly this mass, the first job does the first important thing, that is on the model, Schwarzschild de Sitter space give you exactly what you want, so it computes exactly the parameter M. Okay, so the one harmonic mass on the Schwarzschild de Sitter, lambda M Schwarzschild de Sitter gives you M. And this is the Riemannian Penrose inequality that we were able to prove for this quantity. That if you are in a three-dimensional compact manifold with scalar curvature bounded by 2 lambda, the setting is the one that I was describing before. So the boundary is split into two connected components, boundary of M minus and boundary of M plus, one of each is the boundary of M minus has less area than the other. suppose that there are no closed minimal surfaces in M minus the boundary. And again, these are sort of hypotheses on the boundary plus and the boundary minus that are similar to the sort of asymptotically flat setting, okay? But in this framework, and this is the positive mass theorem in this case. So the M1 lambda, the one harmonic mass, is bounded below by this term, where we recognize the standard Riemannian Peretz inequality in the case lambda equal to 0. Now we recover it in the case lambda equal to 0, but now you have this term more. Okay. Let me comment just a few things. First of all, one of the things that the boundary of M minus being strictly stable gives you is two things. First of all, that this T plus that I couldn't really explain very well before is well defined, but also it is well defined because the boundary of M minus turns out to be less than 4 pi over lambda. And apart from the fact that this gives you that this T plus is well defined, also tells you that this term is strictly positive also. Okay, this term here. And also let me say that this inequality was conjectured by in this paper of Bray-Cruchel of 2004. Actually, but in the case lambda negative and for the total of mass, because as I said this in the beginning, we didn't know. It's hard to find, it was not available yet, a notion of mass in the context of lambda positive. So this conjecture in the case lambda negative and for the total of mass that tells you exactly the same thing is the only thing that was available in the literature. Okay. So now let me explain you a little bit how we could derive this one harmonic mass from corresponding p harmonic masses. Okay. So we, as you see, the quantities before are essentially are geometric. We come from a more functional setting. So the setting is the one as, so think of more than the Riemannian Peretz inequality setting for the moment, think just of the positive mass theorem setting. So you have just one boundary, one connected boundary of a free manifold with the normal hypothesis with the scalar curvature bounded below by 2 lambda. Now, in this manifold, we pick a point, okay, x, and we define on it the p harmonic function, actually this p Green's function defined in it with 0 Dirichlet value. Okay, this is just a schematic picture of the Green function, and it's also very important to associate to it, and I will recall later why also it is important also for concerning existence of the inverse mean curvature flow, this function associated with the p harmonic function. Okay, if u is the p harmonic function, is w is 1 p minus 1 log of u, this satisfies this corresponding problem in M, okay? So u goes to plus infinity at the pole and 0 at the boundary, vice versa, this w goes to be minus infinity at the pole and towards the boundary goes to plus infinity, okay? Good. These are the quantity that with some effort we were able to find and prove that are that actually were good in the sense that they give you a positive mass theorem attached to each p harmonic function and the corresponding WP function. Okay, so here let me first comment. Okay, the perimeter of omega tau p. Here p stress the fact that it's associated with the function UP or WP. Okay, solution of the p problem. So omega is in any case the sub-level set of W with respect to tau. There is the mean curvature, there is the function U, and some constant, positive constant here that are that have a more or less explicit actually expression. Here you can also find R lambda, which is the radius of your model solution. Okay. And there is also another thing that for the moment I will not comment, which is this little lambda. It's very important. This is a function with this little lambda, this a functional parameter that has not to do like, with the capital lambda, and I will tell you later its role. Okay, so let me now recall what is another important connection, because we are going to see that also through this correspondence, actually we will be able to derive formally from the p harmonic masses the one harmonic mass. But before arriving to it, let me recall you this important result. The fact that through this change of function, it is possible to prove, and this was the first result in this direction, was the one of Moser in 2007 in the Euclidean space, to prove the existence of the inverse mean curvature flow. To prove that by proving that these WP functions converge locally in L infinity compactly L infinity lock, sorry, to the solution of the inverse mean curvature flow. And then other results was generalizing this first result in the context of sectional curvature that were bounded below, but then by Mari Rigorisetti with Ricci bounded below. And also the same kind of existence proof with the use of this what is called now more and more in the literature, these are called P inverse mean curvature flow function, this P inverse mean curvature function. They were proved in the recent result of Benatti, Mari Rigolisetti, and Xu, that they also converge locally on compact set with respect to an infinity norm, with the continuous norm to the inverse mean curvature flow with obstacle. Okay, so there is this existence result. Now, let me now comment on this function little lambda here. So it is important that the little lambda satisfies what is called what we call a structural ODE system, where there is not just lambda appearing, but most importantly the mu function that then in the expression of the total mass do not appear, but it will appear as in a sort of limit. And in this structural ODE system, which is actually decoupled ODE system, because you just have to solve it for mu, which is a Riccati equation for mu, and then solve it for lambda. There is also this function alpha that I will comment if I have time later on it. But so for the moment, let me just say that lambda here satisfies this ODE system. And so what we could prove about the p harmonic function, these p harmonic, total masses, is that first of all that it is finite. It's not, and this is due to the asymptotics of this lambda function at minus infinity and at plus infinity. Okay, and it satisfies the positive mass theorem that characterizes the de Sitter spatial manifold. Okay. What I wanted to tell you about was how we could derive once we had, which is the biggest part of our analysis, once that we had this P total masses, how we can derive the one total masses, okay? So for things like the positive mass theorem, also to say, okay, but this mass is finite. As I said, at every P fixed, we have to study, it was not really so easy, the asymptotics of this lambda function at minus and plus infinity. But another thing that we can do is to fix tau and see what is the behavior of this function as P goes to 1, okay? So to see this, let me tell you the following. So let me rewrite now the p harmonic mass in the same setting, but supposing that the boundary of M is minimal. Okay, so there is this term here that cancel. So in the case where the boundary of M is minimal, my p harmonic total mass is this. So it contains all the same ingredients. There is this lambda function. I'll rewrite some things depending on P, because now it's really important for me to stress the dependence on P, on these quantities, okay? So what we could prove is that this constant P, actually, it goes to 0 like that, as P tends to 1. And also that the e to the lambda P tends for every tau fixed to this limiting function here. So to the function e to the tau over 2, just if tau is before this threshold here, 2 log of r, and 0, okay? So now what happens? We can try to formally take the limit of our quantities now as p tends to 1. So in order to do this, we need a bunch of hypotheses. For example, suppose that the gradient of the UP at the boundary is bounded above by the same Dirichlet energy of the model solution up to some constant which do not explode faster than 1 over p minus 1 goes to as p goes to 1. It's a sort of reasonable assumption. And also suppose that you can prove this. Now, these two are sort of assumptions that you can do, which are reasonable assumptions. This thing is something that probably can be proved, and probably can be proved how this behavior, this L1 behavior of the, sorry, here there is something missing at the perimeter I was mentioning, not just maybe this Alessandra Cruda and Benatti Pozzetta can prove that in a sort of very false sense you have a convergence of the level set. But here I wanted to say that what we need in order to pass the limit in our P energy as p tends to 1 is that the perimeter, sorry, the perimeter is missing, is tending to the perimeter of the inversely curvature flow with obstacle as p tends to 1 in the L1 sense, okay? In order to make this passing to the limit here, no? And so supposing this reasonable assumption, suppose that you can prove this, maybe it's possible. The limit of your P quantities is the one harmonic mass that I was showing to you at the beginning, okay? So you see, now you see why the fact that the time is at some point blocked at this threshold comes out, no? Because exactly from this, because at the P level, you have to take the integral among all the values of your WP function, which ranges in between minus infinity and plus infinity. But when you take this exponent e to the lambda p tends to the corresponding tangent as p tends to 1, you have this flattening that happens from some time on, okay? And so this is the one harmonic. Now, I have I don't know if I have a few minutes. Okay, now the idea was to introduce now the construction of the P harmonic function, because as I told at the beginning, I'm doing really in the opposite way we derive the things. So also before arriving to the P total masses, we defined some quasi-local P total masses, meaning some quantities associated to each level set of our P harmonic function. And so the construction starts like this. So suppose that you have a band in your manifold, you have an object, an omega with two boundaries, okay? It's useful to do this, to develop some general monotonicity formula on a general band like this, because then what I will do with this band, the one boundary will tend to a point, and then the other boundary I'll make it tend to the boundary of the manifold. Okay, but let's develop the monotone quantity on a general setting like this. So you have your manifold, and you take a domain inside with two boundary components, okay, and you solve these problems. Okay, the problem for you, so U is P harmonic in omega with a suitable Dirichlet value, and the corresponding problem satisfied by W, okay, which is this in this case, okay. So attached to it, each level set of the W function, so which range from S, capital S and capital T, we find this quantity here. So and exactly it's here where I wanted to arrive, because of the question of Felix, because okay, we are going to see that this quantity is monotone, and then the P total masses will come out as a limit as t tends to plus infinity of this function here, essentially. And so you will see that here there will be this surface integral that will go, okay, the asymptotically flat end of your manifold, or in our case to the boundary of our compact manifold. But this will be, this bulk term will remain. This is the bad term that you are using. Okay, actually, yes. Okay, so these are monotone. Why? As you see, these initial masses, okay, they are not total masses. They can represent, for the properties that that we can prove, they can represent a sort of a notion of the mass contained into the level T of your function, into the sub-level T of your function, okay? And they also support somehow the notion of being quasi-local masses, because we can also prove that they satisfy a sort of small sphere limit, okay, according to the postulates of Bartnik. So this, the fact that they satisfy a small sphere limit is a very good thing about for being a good local mass. It's something that you have to satisfy, and this satisfy this property. If t tends to minus infinity in this case, because when t tends to minus infinity means that I'm shrinking to a point. They satisfy small sphere limit. And so this is a sort of quasi-local mass associated to the level set t of your W function. And here you see, okay, lambda is the cosmological constant. Here, okay, I've always written the perimeter of the sublevel set here is the area of the level set, okay, but so because suppose that you are smooth somehow, and h is the mean curvature, and there are these two structural parameters, lambda, little lambda, and mu, and these are important. So we want them to satisfy, okay, these structural relations, these structural of the system that I was showing before. But now I can tell you also a little bit more about this in just a second. So here I've just rewritten my mass at time t. So yeah, we have this general monotonicity formula. So we can prove that under some reasonable assumption, these quantities associated to each level set of the W function is monotone, okay, is non-decreasing. Okay, and now, okay, yeah, the monotonicity relies on a few basic ingredients, the existence of a pure harmonic function U, connectedness of the level set of U. For a given choice of a structural coefficient alpha, we need the existence of a global solution of the structural ODE system. Okay, but now what will be important will be to select an interesting alpha, no? Because what I'm saying is that for any alpha which is continuous, you solve this ODE system, you plug into your formula lambda and mu, and this is always a non-negative, non-decreasing quantity. Okay, but now in order to find a suitable monotonicity formula which maybe give you the rigidity in your setting, we have to carefully choose this alpha. Okay, the alpha which is inside the structure of the system. Okay. This is essentially what I wanted to say. An appropriate choice of alpha will guarantee the existence of a global solution. So we need mu and lambda to be defined on all the interval where interest D. The possibility to select among the global solution those that are effective in obtaining positive mass theorem. Okay, such as example. Okay, so in order to explain these, I think I don't have any more the time, but yeah, just quickly, this is the derivation of the quantity we are interacting with in the model case. So here I was also put inside the case lambda equal to 0 because it is a reference model also for the derivation of this lambda and mu parameter. And this is the exact solution in the model case. What are these functions u and w in our model case? Okay, so this is our p harmonic function in the model case, and this is the corresponding w function. Okay, and now if you take our monotone quantities, if you take the derivative of them, okay, the derivative we can prove that is always non-negative, okay, we can prove that is generally the quantities is monotone, but if we want that if you want to have some hope to characterize your model space, first you want that on your model space this is 0, and in particular you want this term to be 0. So how we select alpha? We select alpha in such a way that it corresponds to alpha over 2 grad of W in the model case. So this is essentially the way we choose alpha, okay? So we impose alpha to be like h over 2 grad of W, where h is the mean curvature and grad W are those of the model space. Okay, so we have to extract the most possible information of this in order to do a suitable qualitative analysis of our ODE system and extract the information regarding the solution lambda mu of the ODE system. Okay, so I think now it's late. Unfortunately, I couldn't show you the way we were selecting the solution because the ODE system has a lot of solutions. There was one particularly nice. It was nice to tell you, but there's no time. And so I will just conclude with this because there were a lot of many things with this sort of selection drawing. And thank you for your attention.
Do we have time for a quick question?
Medium is a non-boundary condition. It's a DC.
What's your question? Yeah, actually, it's not really a Neumann. Maybe you are referring to the one of the inverse mean curvature flow. Yeah, it's not really a Neumann. It's more like because it's more like a relaxed Dirichlet boundary condition in the sense that one can find in the paper of Xu. But it's true. Yeah, the inverse mean curvature flow does not contain a real Dirichlet, but that condition that says that now the level set arrives tangentially at the boundary, and you can somehow recovering this from some Dirichlet problems. At the P level, you solve some Dirichlet problem, and then you can because in fact, as I was showing, you could see it. Our solution, the P harmonic function, the WP function, are all solution of a certain Dirichlet problem, but you can show that they converge locally on compact sets to the inverse mean curvature flow with that condition of the boundary.
Have you any possibility of remove the P, even or less of the P?
If I can remove the P.
The restriction about P.
About P. Actually, I think it's interesting to see also for other ranges of P, actually what we can say. But the fact is that you see, when you change P, when P, for example, goes from 3 on, you can do, I think, a similar analysis, but you have to change it a bit because your model solution changed. For example, in the case P equal to 3, your harmonic function is a logarithm. And so you have to rewrite all the things carefully. Okay, and you can do also the analysis for P greater than 3. For example, the monotonicity holds up to P equal to 5. Maybe I didn't want to stress this fact, but the monotonicity, the general monotonicity for a general alpha parameter holds up to P equal to 5. But then actually, in order to then have something related with your model, you have to restrict to P less than 3 because your model changed when P is from 3 on. And also, we were thinking of this. At some point, we just wanted to do the analysis for every P fixed, but then at some point, we thought that it was very nice to see what happens for P going to 1. So this is why we stopped thinking of what happens. That could be interesting to see.
The question is about when P goes to infinity because we can.
Yeah. So clearly. You have to change a bit your model. Yes.
I need to see if I understood. So, so you have not given a precise definition of what is a proper solution in the compact setting of a investment. But if I have understood correctly, so this new version with obstacle allows you to base the equation for of the manifold, and the previous case didn't.
Yes, Allora, this inverse mean curvature flow with obstacle is the ingredient that we need to define this one harmonic mass. Then we can also show that this one harmonic mass is a formal limit of some p mass.
No.
But let's stay on the one harmonic mass. Once you have this concept, this is not due to us, it's due to Kai-Su, you can use it to define the one harmonic mass. But now consider that this is an existence result, not the one of Su. That's very beautiful paper, but there was no concept of mass. So it was different from the inverse mean curvature flow, because the beautiful paper of Wisken was checking a monotonicity of the quantity was already given. It was good in order to find the total mass, which was the Hawking mass. But in this case, this was not like this, because maybe I didn't say this, because I said at the beginning how the Hawking mass does not work in this context with the inverse mean curvature flow. But you could say, but maybe the Hawking mass works with the inverse mean curvature flow with obstacle. No, there is a counterexample. Okay, so the problem here was the development of a quantity. New
No, this is absolutely clear, but I want to understand what.
No, to prove the existence is proved in Kai-Su. And Benatti, together with Su and Rigoli, they have proved that you can also prove the existence via this limit on compact set of WP functions. But
We will here.
we
construct it right by here in that case of course.
I don't know what, yeah.
We discuss.
Okay, so we will have time to finish the discussion. So let's start with senior.